Well, in this session, we'll continue analysing whether the incoming wave function gets reflected or transmitted at the barrier. In the case when the energy E is larger than the potential V0, the finite potential at position x is 0, right? Okay, so when the energy E is a lot greater than the potential barrier V0, so E is much greater than V0, then K dash, go back to the previous session, you'll see that K dash effectively just becomes almost equal to K. And if that's true, again from the previous session, the percentage, well the fraction of the flux that gets reflected, called R, big R for reflection, that effectively goes to 0, as you'd expect. This highly energetic wave meets this very small barrier. And it behaves as though the barrier almost is not there, right? So very little gets reflected, and T, that's the fraction that gets of the flux that gets transmitted, approaches 1. So that's what you'd expect. Okay. Now, but the particles that do go through, they go into the barrier. Classically, you'd expect those particles to be less energetic, right? They lose some of their energy because they've gained potential energy because of the V0. So the kinetic energy should decrease, hence their momentum should decrease, and that makes sense because because K dash will be less than K. I'm remembering now, I cannot point to something outside the current rectangle, the current session. But if you look at the previous session, if you look at the formula for K dashed, I'll just read it out. So it's the square root of 2m into E minus V0 over h bar squared. Well, if V0 is finite, so E minus V is smaller than just E, right? Common sense. So, but K is just square root 2me. So K dashed will be smaller than K. Yeah. K dashed will be smaller than K, right? Yeah. Well, if you multiply both sides by h bar, you'll get h bar K is less than h bar K dashed is less than h bar K. Now h bar K, what is that? That's the momentum. That's the de Broglie momentum of your wavicle, right? So this h bar K dashed, which wavicle is that? Well, that's the wavicle in the potential barrier, the transmitted one, the one that went through. Its momentum, h bar K dashed, is less than the momentum of the incoming wave, right? So, so that makes sense, right? Okay, well now let's take a case or subcase when the energy E here approaches the barrier side. So they're pretty well equal. What would you expect to happen then? Well, as E becomes V0, again you can't see it, but K dashed from its definition, have a look at the previous session, K dashed becomes 0, right? K dash, so as E approaches V0, K dashed approaches 0. And if K dashed is 0, big T, the fraction that gets transmitted, of your flux that gets transmitted, big T, again, look at the previous session, well, I'll just read it out to you. So big T is equal to 4K K dash divided by something. Well, if the K dash goes to 0, T goes to 0, right? So nothing gets through. Well, I mean, effectively, the fraction that continues on, well into the barrier, goes to 0, right? So none transmitted. So so in other words, if T is going to 0, R is going to 1, because remember the two fractions R, big R, plus big T,
must equal 1. So if t is going to 0, r must be going to 1. So that means, now what's big R? Well, that's the fraction of the flux that gets bounced back, right? That gets reflected, R for reflection. So so as E goes to V naught, your R, I haven't written here, but your R will become 1. It all gets bounced back, pretty much, which is sort of what you'd expect classically, right? Okay. Okay, now let's do the case when the energy is actually less than the potential, the finite potential. So E is now less than V naught. Well, in that case, your K dashed, which is square root of 2m into E minus V naught. Well, if E is now less than V naught, and you've got a square root there, your K dash now is a pure imaginary number. What's that? Well, an ordinary complex number, its general form is of the form a plus ib. Okay? But if a is 0, then your complex number is just ib, or bi. Well, that's what's called pure imaginary. There's no real part. There's no a. It's just the b. So when your energy is less than V naught, then your K dashed, from definition, have a look at the previous session, is pure imaginary. So it's of the form some real number times I. Okay. So if that's the case, now you've got a formula for B over A from the previous session. And your K dash now is a pure imaginary number, so let it be, I don't know, I P, or I don't know, just I something, I some times some real number. Well, plug that I real number into your formula for B over A and square it, and you'll get 1. So again, sort of homework, right? So B over A squared, if that's 1, what does that imply? So if B over A squared is 1, what does that mean physically? What's going on? That means that everything's reflected, right? It means the amplitude coming in is equal to the amplitude going out. So that means everything that's coming in is going out. So everything's getting reflected. Nothing's getting transmitted. Okay. So that means R goes to 1, and therefore T, the fraction that gets transmitted, that goes through, goes to 0. Right? So if R goes to 1, T goes to 0. Right? So all your particles are reflected. But interestingly, the wave function on the right-hand side, to the right of x equals 0, is non-zero. Now, but it does drop off exponentially, very fast, right? You can let's see, where's this one? Equation plus. Okay. In the previous session, have a look at your equation for the wave function to the right-hand side, for x positive to the right of the x equals 0, and you'll see, given that k dashed is I times some real number, I call it A, or D if you like I, D, then that wave function is proportional, or let's call it K, right, instead of little big K, let's say. So your little k dashed is I big K, right? So plug that I big K into your K dashed in your formula in the previous session for the wave function on the right hand side, x is positive, and you'll get something that's proportional to e to the minus bkx. Right? So your wave function drops off exponentially, very fast with distance. Now the other term in your wave function, because d was 0, right? Yeah, because big D was 0. Okay, right. So what that means is, because of this, I mean, it exists. It's not zero. I mean, it drops to zero very fast, but still, there is some of your wave function that exists to the right of the barrier. Right? It decreases exponentially very fast. But that means the particle does penetrate a short distance into the barrier. Right? So there is a finite probability that happens. All right. Now, here's another case. If V naught is